space. A lot of games take place in space. And also, a lot of games are 3D these days, but weirdly, for some reason, not a lot of games that take place in space actually show you space in 3D. Quite often when we are shown a map of 3D space, that map is actually not 3D. For instance, in Mass Effect you're shown the galaxy, but it's just like a flat galaxy that's just a little bit tilted, so it looks a little bit spatial, but all of the points are on the 2D plane. And it's the same thing with even like a complex game like Stellaris, where you have essentially a flat map where the stars are moved just a little bit up and down, so it looks a little bit three-dimensional, but it's not. For some reasons, games are afraid of showing you space in 3D. Fine. I shall do it myself. Hi everybody, welcome. I'm Christian, this is LazyDev's Academy. Welcome to this instructor pod on how to make a 3D map. Before we begin, 3 little disclaimers. I will be working in Picotron and an engine called Picotron, but everything I say today will apply to other engines as well. More specifically, there will be chapters down there, and at some point we will take all of the code that we have here and we move it over to Pico-8, because all of the code that we do here today will just lift straight into Pico-8. We're going to see how that works out. Hopefully there's going to be minimal adjustments that we have to do. But even if you're working in a different engine, some of the stuff I talk about today will also work, even if you're working in a 3D engine like Unity. You just have to like push the 3D stuff to the side and focus on the astronomy part. Second disclaimer, so this is going to be a bit of an introduction to 3D, to making 3D on your own, like from scratch. But we are cheating a little bit. We're going to make baby's first 3D, so this is going to be a simpler kind of 3D. We're not doing real perspective projection. We're just going to do like an orthogonal projection. And I'm going to show you what that means. So here I am in Blender. If you don't know about Blender, doesn't matter. I just want to showcase like what the difference is. So this is regular perspective projection. You can see there's a cube and there's a cube in the distance there. They're both the same size, but obviously the cube in the distance is smaller because it's further away. That is perspective projection. That is not what we're going to do today. What we're going to do today is orthogonal projection. We're going to click on here, boop. And this switches us to orthogonal projection. And as you can see, those cubes are now the same size, even though one of them is further away than the other one. It's kind of like a projection as if you're very far away and very strongly zoomed into the scene. It's the same kind of projection that you get from, strategy games like Final Fantasy Tactics, for example, has like this kind of projection, I think. In pixel art, you quite often also say isometric projection. That's what we're going to do. That's easier to pull off, and that's also kind of like fitting for a 3D map. I think for mapping stuff, it's good because it doesn't distort distances. And the third disclaimer is that everything we're going to do today is going to be a little bit, we're building things from first principles. It's not going to be efficient in any way, shape, or form. The goal is not to make an efficient, fast 3D engine. The goal is to provide us with an understanding of how 3D works and give us kind of a mastery of the system so we can later on then build upon it and enhance in the future. That's maybe something for a different video. Which is why I also won't be using stuff like matrix multiplication and all the fancy new stuff that was introduced to Picotron. Not just yet. First of all, let's get started with the basics. So we want to do a 3D map, and we want to do not just any 3D map. I want to do a 3D map of the actual nearby stars in the real world. Isn't it a little bit strange? Isn't it a little bit funny that if I ask you to name planets of our solar system, you will be able to name a whole bunch of planets. You get them listed in children's books. You have beautiful illustrations of our solar system. There's Jupiter, there's Mercury, there's Mars. We have Sailor Moon. But if I ask you to do the same with nearby stars, how many nearby stars can you name? Maybe like Alpha Centauri? That's like the nearby star. There was a video game about it. It's great. But like, what's the second next star? And what's the third and fourth? Like, what are the nearby stars? How does it look like nearby? It's kind of weird that we don't know about these things. This is not broadly communicated. And it's kind of even like difficult to access information. You can pull up charts online, but they suck. What is this? What am I supposed to do with this? Ah! This one is a little bit better, but also like it's just points floating in space. Like I don't have an idea of where things are. And then if you zoom out, it's like, this is a trip. but it's not really a map. That is also one of the reasons why I want to do it ourselves, so we have full control over the way things look, and we can even utilize it. We can actually use it later on maybe to create games on top of it. But let's not get ahead of ourselves. Let's get started. So I'm gonna save this as star map. And then look, I have special powers. I can just snap and I will create our first 3 functions. Ha, that was easy. So we have init, update, and draw. And we can get started right away. So first of all, let's make everything black. Space is black. You can make space different colors. I think blue is also a good color, but the problem is that in Picotron, we don't have too many colors at our disposal. We can have more colors, but I don't want to go there for this tutorial. Right, so in order to get started, we want to have 3D data. 3D data means Cartesian coordinates, so if we have X and Y, and then we have Z. And those 3 coordinates have to be turned into 2 coordinates. We have to put them on the screen because our screen is just 2D. So we project 3D onto 2D. That's what 3D games are. And the easiest way to achieve such a projection is just to ignore one of the coordinates. That's going to be like a flat, for example, if you have a 3D map or something, you just look flat from the top. You will just ignore the height on the map, right? That would be a simple projection. And we're going to start with that, and we're going to see where we can take it from there. So let us create a cube in 3D space so we can see a 3D object, right? So I'm going to define an array with edges, right? These are going to be edges, and each edge will be an array. So it's going to be an array of arrays, and each edge will have 2 arrays inside of it. There's array of array. And so there's going to be the beginning and an end of each edge, right? And then inside here, we're going to put in the coordinates. For example, we're going to start with 10, 10, 10, for example. And then we're going to go to minus 10, 10, 10, right? So that's going to be the first edge of our cube. Let me finish up the rest of the cube with a snap. All right, we're gonna see if this works. So how many edges are on a cube? So we have like 4 on the top, 4 on the bottom. So that's 8 edges plus 4 on the sides. So that should be 12, 9, 10, 11, 12. I think at least the number is correct. We're gonna see if this is a cube. All right, so we have the cube now. Let's draw the cube to the screen. For E in all edges, do. And then we're just going to do it in the most stupid way possible. And then it's going to be wrong. And then we're going to fix it. Let's go like local start equals E1. So that's going to be our starting location. And then I'm going to do an end. Well, maybe let's go with E end and E start. So it's a little bit, so we don't have any problems with end. And then we're going to do the line now. So we're going to do a line between E start. And then that's going to be the first coordinate, the second coordinate. And again, we're going to ignore the third coordinate for now. The color is going to be 12 for now. Or we're going to change it later on. E end. And then E end. And it's going to be 2. And there's going to be 2. Right, so just taking the first coordinate and the second coordinate of each of those points. And that's gonna be it. That's all we need. That's all we need. We're gonna run this. We have a square, ladies and gentlemen. It's all the way up in the corner, losing its religion. So there's a lot of work to do. First of all, let's bring it to the center of the screen, right? And off the bat, I will immediately already start thinking about projection. So we're gonna create a function called project. Project, and we're going to go P1, just the point P, and then that will return a projected point. So that will take in a little array with 3 values that has X, Y, and Z, and it will return a different array that has just 2 coordinates like X and Y. It will turn 3D coordinates into 2D coordinates on the screen. Makes sense, right? Local ret p, that's going to be our return value, right? And then we're going to go ret p equals. So again, we're just ignoring the the z coordinate for now. We're just dealing with x and y. And then again, we're gonna improve things later on. So we're returning this point now, and then that allows us to do the projection. We're gonna see in a second why I'm doing this. So we're gonna project this point, we're gonna project this point. So far the same thing, we're gonna run this, it still looks the same, but now this allows us to now manipulate the return x and y that is consistent across the board. And what I want to do here, I have written down the values. I want to add something to the x and y position so it's a little bit more centered on the screen. Very simple. So we're gonna do something like ret p1 plus equal this, and then ret p2 plus equal this. That will make things a little bit centered. Like this. And then we have a little square in the center of our screen. How beautiful is that? Now, I would love to be able to maybe like, because it's a small rectangle right now, right? It would be nice if we could maybe zoom in. So let's see if we can make it so that we can zoom in and look a bit closer. Because I will tell you right away, we need to like manipulate the star map. The whole point of the 3D star map is that it is interactive, that we can look at things from different perspectives. So I want to zoom in. And I'm going to do this right here. So we're going to go, we're going to get the mouse position for now. And also we're going to go mouse button. We're going to do that at some point. But also mouse wheel X and mouse wheel Y. So these are a whole bunch of variables and we can get them with the mouse function. The mouse function just returns a whole bunch of variables that tells you about what the mouse is doing. The thing that we are most interested about is the mouse wheel Y. That will be set to a value when you are using the mouse wheel, and we can use the mouse wheel to zoom in and zoom out. Now that also means that we need to create a variable for zooming. Let's call it cam zoom. And let's set it to 1 for now. And so in the projection, we're already going to apply this. So we're going to say something like, before we do this, we're going to go ret p, we're going to take the x coordinate, and we're going to multiply it with cam zoom. And we're going to ret p2, and we're going to multiply it also with cam zoom. So now this cam zoom variable will now modify how big the rectangle will appear on the screen. So now all that is left for us to do is to kind of like make sure that, you know, we're zooming. And I'm not sure exactly how to do it like with a formula, so I'm just going to use an if statement. So if mouse wheel Y, if that's smaller than 0, then, and then we're going to zoom in or up. I'm not sure exactly which way is up and down. And then else if mouse wheel Y is greater than 0, then, so this is for zooming in the other direction. And then here, just let's say equals cam zoom divided by 2. And then here's cam zoom equals cam zoom times 2. Oops. So cam zoom gets bigger and smaller when we're zooming with a mouse. And look at this, it's working, it's working. We have powers of 10 already, if you know that reference. Okay, so we can zoom in right now, that's fantastic. Okay, I want us now to get a little bit complicated. We can zoom in, but obviously something that we will have to do at some point, not right now, but at some point, we want to be looking at the 3D map from different points of view. So we have to rotate the 3D map. Right now it's a 2D map, right now it's just a square, right? But I want to also already use the mouse to rotate the square. Can we make it so that the mouse rotates the square? Can you just make the square just rotate? For now, just make the square just rotate. How do we do that? Well, first of all, we need to create a variable that tells us how much things are being rotated. I'm going to call it cam rx. I'm not sure if x is the correct term, because technically we're rotating it around the z-axis. But I'm using X because we're going to move the mouse sideways to rotate it. So let me just cook. All right. So then every frame For now, we're just going to slowly make the thing rotate, right? So we're going to go plus equals 0.01. So very slowly, I guess. Hopefully it's going to be slow. So this variable now counts up and it slowly rotates. When this variable, like the units of this variable are going to be the Pico-8 radians, which means that 1 is a full rotation. So 0.01 is like, I don't know how many degrees that is, 3.6 degrees, something like this. I think it is. So maybe it's a little bit fast. We're going to see. So now what we need to do is we need to make sure that this cam Rx will actually rotate all of the points here in the project function. So in the project function, we're going to take the locations of where the points are in space, and we need to rotate them around the center of the coordinate system. And that's actually easy to do. There's a formula. You can look it up. So let me look this up. So it's RP1, so we're going to take this coordinate and we're going to multiply it by the cosine of cam Rx. And then we're going to subtract from this RP2 multiplied by the sine of cam Rx. Right, so that's the first formula, and the second formula is for the y coordinate. Again, we need to just move things around a little bit. So this time it's going to be sine, and this is going to be cosine, and this is going to be a plus. It's a formula. You can look it up. How do you rotate a point around the origin of the coordinate system? That's the formula. Now you can see already this is a little bit of an inefficient thing because we are calculating the cosine twice per point and the sine twice per point. We're going to fix this in a second. But first, let's see if this works. Oh, it's not RP, it's red P. Why did I write RP? Red P. I'm sorry. Okay, let's try it now. Hey, what? What is happening? Oh! You will not down before me, Jarrell! We are in the shadow zone. We are in the shadow zone. Oh no. Something is not working the way it's supposed to work, but I love it. I know what the problem is. The problem is that, the problem is that we got input and output variables confused. We want to store the results of the rotation in the red P list. But as you can see, we are actually performing the calculation with red P as input. This is wrong. You're supposed to do the calculation with the pre-rotation coordinates. Now, funny enough, this kind of still works for the first line because we actually pre-fill red P with those coordinates. But once we get to the second line, we are feeding the results of the rotation back into itself, and we get that cool phantom zone effect. It's phantom zone, right? Anyway, we need to fix that. Oh, and while we're here, I'm not proud of how I defined the red P object twice before here. That's embarrassing. You've seen it, I've seen it. Let's just move on and not talk about it. I think a good solution for this is just to work with P directly. Let's see if this will solve the problem. Very nice, very nice. So now we have a little rotator potato happening, and we can zoom in, and isn't that nice? So now let's make it so that it responds actually to our mouse movements. It's not just rotating on its own. Okay, so we're doing this like this. So if we're going to go if MB, so if the mouse button is greater than 0, so if it has been pressed, then. Now, what I want to do now is I want to kind of like track of how much the mouse has moved since the last frame. Because like if you move the mouse quickly, want to rotate quickly, and if you move the mouse slowly, then I want to rotate slowly. So I kind of want to see how much the mouse has moved. In order to do that, I think we need to create a variable for this. So we're going to go last mouse X, last mouse Y, right? We're gonna do something like this. And if I click, by the way, at the end of the update function, last mouse X and last mouse Y, I'm going to set to MX and MY. And then if the mouse button is pressed, on every frame the mouse button is pressed, I'm going to modify the cam Rx, the rotation, with how much I move the mouse. So it's going to be something like plus equals MX minus last MX. And then we have to make it probably a bit smaller because like 1 pixel would be a full rotation. That's a little bit fast. So let's multiply by a huge number, divide by a huge number like thousands or something like this. So that should give us, and as you can see, we can rotate a potato, this beautiful, beautiful rectangle. Now, so far so good. We can zoom in and we can rotate stuff, but where is the 3D? Christian, you've been promised me the 3D. There, it's just 2D. It's a square. We're rotating a square. I want a cube. Look, I created all of these 3D coordinates. Where is the 3D? We're just ignoring the third coordinate. Justice, bring back the third coordinate. Well, don't you worry about that. I talked about how orthogonal projection is a little bit, but not quite like isometric projection. Isometric projection consists of like rhombus-like situations like this, and then you will have like a house on this. So that's what we want to have. Currently, we have this. We have square, right? And we can rotate a potato this square, right? So that's currently what we've been working on. Can we rotate a potato? Is that something that you can do, Paint? Okay, it looks like Paint cannot rotate a potato. So we rotate the square into this shape, right? We rotate it into this shape. In order to get to this kind of perspective view, to get a kind of like oblique isometric view, what we need to, it seems like what we need to do is we need to just squish it together, right? Then that will get us to the isometric view. We need to squish it together. But technically, yes, that's true, and we would get a bit of a squished image, but we wouldn't get the 3D shape that we have here because we also have, for example, this house on it, right? And from the top view, this house will look like this, right? So the house wouldn't come off into the 3D space if we just squish it. Yeah, so actually what we need to do here is to do another rotation just along a different plane. Previously, we did a rotation along the X and Y plane. Now we need to rotate in a Y and Z plane. And this is what it would look like from the side. We need to tilt our 3D object into an oblique view, into the screen, so to speak. Now, if our object was just a flat rectangle, it would look as if it was squished. But since our actual data has some depth, you know, some points have different Z coordinates, some points are in front, some points are in back. This will mean that after rotation, some points will appear to move up and some points will appear to move down. And this will give us this spatial 3D effect that we're looking for. One thing to note is that we need to calculate only the Y coordinate this time around. This rotation will move the points up and down on the screen, but not sideways. This is, among other things, thanks to the special orthogonal projection that we're using for this project. This just means less calculations for us. Yay! Alright, but now we're rotating in a different dimension, so let me first create a new variable for this. So this is going to be cam_ry. Cam_ry. Something like this. And then I'm going to use the same function that I use for X. I'm going to use for Y as well. And it was going to use something like this. Right, so now what we need to do is need to actually get the formula for the Y rotation, for the second rotation that we do. And we're going to actually use the formula that we already have because it's the same type of rotation. In order to determine the Y position, we use this formula. And now we kind of like adding something to the Y position. Something might move up and down additionally because of the second rotation. So we're just going to copy this formula over here. And then we need to change some things. First of all, we need to substitute the second angle because now we're rotating with a different angle, right? No longer like this, but now like this. And now we need to also substitute slightly different variables. This variable, instead of the X, we're going to use Z. So this is going to be 3. And this, instead of the original Y position, now we're going to use the already rotated Y position. And that has to do with the order of things. First, we need to rotate this, and then we need to rotate this, you know. We could do it the other way around, but then that would be wonky. Don't you worry about that. It's fine. And I think that's going to be it. So let's save this. Let's run this. Whoop, whoop. Hey. Let's go, baby. Let's go. What's good? That's our 3D cube, baby. Now you immediately see some problems with the orthogonal projection. One of the problems with the orthogonal projections is that it's really easy to mess up your coordinates because, like, you get like this optical illusion where you don't quite see where is front and where is back, because you literally don't have any clues where front and back is. And in some ways, it doesn't even really matter. It's kind of like a matter of how you imagine things. That's why being able to rotate with the mouse really gives you a hint of what's happening, because it feels like I'm dragging the cube around, and that allows my brain to understand this spatially better. So the fact that this map is interactable is very important. Once I stop rotating, I get the optical illusion problem where I don't quite know how the cube is oriented in space. But yeah, that looks sick as heck. Now let us talk a little bit about dimensions, about coordinate systems. In fact, let me tune this a little up. These edges, I want to maybe encode the color of edges as well. So let me put 12 in here as the third, the third entry in an edge. And that way we can color the edges if you want to, so we know exactly where it's up and down and so forth. And then where we're drawing them, instead of just drawing flat the 12, we're just going to get that from our edge. So it's going to be E3, right? So now it's the same thing, but now one of the edges will turn red. And you can see one of the edges is now red. That's neat. That's neat. We can now color the edges a little bit. And I'm doing this mainly so we can do like a little test. I don't know what it's called, coordinate system, so we can see where the axes are in our coordinate system. Let's run this a little bit. So you can see, yes, something is wrong here. There we go. There we go. Yes. So you can see how now some things are not right here, because right now Z is pointing down, right? I want Z to be pointing up, so that's not quite right. And then the green line, that's Y, and the red line that's X, right? So it makes sense, like Y is pointing down, X is pointing to the side. Let's make it so that Z is pointing up. That makes no sense to me. And I think I know what the problem is here. So let me actually draw the rotation angles of our camera, so we know exactly how we rotated the camera. Let me do like a cursor. Let me put the cursor at 5, 5. Let me do a color 5. Let's go 5. And then let's print. I want to print cam RX. I want to do it ... And then RY like this, right? So we know exactly what the rotation values are. And as you can see, the problem is that we're getting into negative. When I move the mouse up, I kind of rotate in the wrong direction. I kind of like rotate underneath. So that's why it's like, I'm kind of like rotated it upside down. So I'm not sure exactly why that is. It could be also with the sine and cosine. Who knows? Who knows? It works better if you do a minus in here. So now you can see, now if I rotate up, now if I rotate up, the Z is pointing upwards. So that's what I want. I want positive values to go up. That makes sense to me. That positive goes up. I don't know. I know that on the screen is the opposite, so that's why it's a bit confusing. That's why maybe there is a bit of a disjointment here. But yeah. Now one thing I want to maybe add in order to avoid this confusion in the future is I want to maybe clamp the X rotation, the Y rotation between looking from top and from the bottom. I don't want to rotate so it's upside down, because that gets confusing, right? So let's go cam RY equals mid 0, cam 1 RY 0.5, I think. I'm not sure. let me try it out. Okay, so you can see, yes. And now we're looking from the bottom, and now it doesn't rotate any further. So we physically cannot rotate the camera upside down anymore. So that's good. So this gives us the coordinate system. Now let's compare with the coordinate system cheat sheet. So if I'm looking at this, so Z is up, definitely. And then let me see. So it's a little bit complicated, but we are right-handed and Z is up. So we like in 3ds Max, Blender, SketchUp, Source, and Autodesk AutoCAD. That seems fine to me. Okay, 2 more things. I want to make this rotation a little bit more spicy, and I also want to add stars. Let's begin with the stars. So I can remove those edges already, and I will now add stars. And now a star is just going to be a point in space. That's actually going to be a little bit easier than the edges. So let me create like 3 stars. I don't know. I have no idea where the stars are. 1, 2, 3. 7, 4. I don't know what these stars are, but that seems fine. And then here, when we're drawing stuff, we're going to just do the same thing for S in all stars. Do local P equals, so that's going to be my point, and I will just project that star coordinate using the same project function. And then we're just going to do like a little circle. Circ fill P1, P2. It's going to be a little circle. Let's go 2, and it's going to be yellow because stars are yellow, right? It's going to be 10, like something like this. Let's see how that looks. There's an L missing. What? Oh, right. It's just S here. So this time around, a star is just the coordinates. It's not 2 sets of coordinates. So that's why we just put the S in there. And there's our stars. Look, there's our stars in space. Isn't that neat? Isn't that neat? Now, okay, let me actually make a real star map. And this is, this is information design a little bit. Now that we have the cube, that we know everything is peachy, we can think about how to best visualize this kind of stuff. And I think a good idea is to have like a grid. I want to have a plane on the bottom, and all of the stars will be kind of like sticks, will be on sticks sticking out from the grid. I think that's a cool visualization. So let me try to do that for now. So I want to set up a space, a cube that is 14 light years in each direction, so 28 light years in size. And each unit is going to be 1 light year. But we're going to use a bit of a coarser grid on our plane. I will show you in a second. So let's go from -14 to 14. So for I equals -14 to 14. And step 2, do. And we're actually going to overwrite those edges. We're not going to have the cube anymore. We're just going to create our own edges. So edges equals, we're going to clear the edges. We're not going to have the cube. And we're going to go add edges. Something like this. So now we have a little grid in 3D space, and now the stars are kind of hovering above this grid. And as you can see, like this is kind of like already pretty fine grid for this resolution, right? So like if each box in here is 2 times 2 light years, if we made it like 1 box is 1 light year, that would be very fine grid. So that's why I decided to make it a little bit more coarse. I think that's already good enough. Now, again, these stars are kind of like floating in space. Even if I rotate it, it's kind of like difficult to pinpoint exactly where they are in space. So I will draw a bit of a help line to help us keeping track where the star is. And we're going to do it here when we're drawing the stars. I'm going to go local P2 equals. And what I'm going to do now is I'm going to create a new point that is just the X and Y coordinates of the star, but not the Z coordinates. I'm going to project, so to speak, the star on our grid so we can find like the vertical line. So that's going to be something like S1, the X coordinate of the star, S2, the Y coordinate of the star, and then 0, right? So that's where the star is on the grid, so to speak. And I'm going to draw a line between P and P2. The color of the line, I'm not exactly sure. I'm going to set it to 2 for now. Okay, and as you can see, it's the stars are now touching the grid. So now it's way more clear where the stars are on the grid. That is all what we need so far. There's 2 things I want to add to make things a little bit more spiffy. I want to add a bit of a nicer rotation. Because right now it's a little bit like, it's not nice. It's not nice to be rotating. It's not the iPhone way, So I want to add a bit of a inertia to the rotation. I can just flip it and it continues rotating if I release the mouse. So let's do that for now. So instead of the chem RY and chem RX, I also want to save a speed for the rotation. So chem RYX speed. So like this, I want to add second set of variables for the rotations, for the two rotations that indicate how fast they're rotating. And then I'm gonna put them in here, like so. I'm just gonna set them to those. And then here, outside of that if statement, if the mouse button was pressed, I'm gonna go cam rx. Now I'm adding the speed to the x rotation, and I'm adding the speed to the y rotation. I think it needs to be minus for the y rotation. Let me check this real quick. Yeah, this works, but now the y position is reversed. So here we need to go minus. As you can see, we can now rotate a potato. It keeps rotating, so it would be nice if it maybe stopped rotating at some point, right? It would be nice if it stopped rotating. So let's do a bit of a breaking function here. So let's go else. So if we're not keeping the mouse button pressed, we're going to multiply them with a value. 0.9, I don't know. Let's see if this works. Hey, yeah, that seems nice. So now we can flick this map around, so it's more of an iPhone situation. You know how iPhone is. Like the scrolling feels a little bit nicer. That's kind of nice. You can see if I'm looking from below, it kind of gets a bit confusing. We're going to address this at some point, but for now, I'm good with that. One more thing, I told you that I'm not going to do a optimization thing, but there is one thing that I already mentioned. This bugs me that we're doing so much cosine and sine per individual coordinate. That seems wasteful because all of these things have to be calculated just once per frame. So let's just pre-calculate the sine and cosine so it goes a little bit faster. So we're going to go like in the draw function, because here's where we do the projections, right? We're going to go cam rx cosine, cam ry, cam rx sine, and cam ry sine, right? We're just going to pre-calculate all of these calculations. Like so. And so now we can just plug those guys in here. Now I'm paying attention so I don't accidentally. Okay, I think something like this. Let's try this. It seems good. It seems good. Yeah, it looks still the same. That's nice. That's nice and good. All right, so now it's a lot. It runs it's just not quite as wasteful as it was before, because usually like that's why 3D was difficult to do before. We have 3D acceleration. Sine and cosine were very compute intense, and you wanted to always do as little of it as possible each frame, and so that really hurt my soul. All right, so now we're finished with the 3D part of this tutorial part. Now let's move on to astronomy. Let us discuss why I'm doing this in the first place. So there is actually, I did this project a while ago in 2008 in Flash. So, you know, I'm already familiar a little bit with this data set, and I did this based on this Wikipedia contributor. This is Inductiveload is the author of this. This is a very nice map. They created this map already, but again, it's not interactive, so it's kind of like, I also don't like the circles. So it's kind of like a little bit difficult to understand what's happening here, but it's a very nice projection of 32 nearby stars. Let us now get his data into our program. The nice thing about this map is that we have a Mathematica code. Oh, so this is actually the data that he's using, and we actually seeing the calculations that are happening here to get all of the data about the stars plotted on a diagram like this. That's very useful. First of all, let me get this star list here. I'm just going to use those numbers that he is using, or they are using. I told you we're going to learn something about it today, and I'm going to create a new tab for this. We're going to call it Astro for astronomy, and we're going to paste it in here. This is going to be star list. We're going to create a function called make stars. And this function will hopefully take these values in here and I'm going to turn them into beautiful stars. Let me format this a little bit. Now luckily for us, this list is actually quite compatible with Lua. There's just like, there's a semicolon at the end that we had to get rid of. And then some names are escaped for some reason. I think it has to do with Mathematica, the language that the original author is using. We can just get rid of these. It's not that necessary. So as you can see, we have 32 stars plus sun, so 33 stars, I think. And now we need to understand what those numbers mean. All right, everybody, time for a brief introduction to celestial coordinates. So astronomers are people who observe the stars through a telescope, right? So it might not come as much of a surprise that they use a coordinate system to describe where the stars are on the sky, not necessarily where the stars are in space. This is what those numbers are. They are celestial coordinates. More specifically, they are equatorial celestial coordinates. So the way this works is, imagine a huge bubble around planet Earth. And now imagine all of the stars are painted on the inside of this bubble. This is called the celestial sphere. And the numbers are just coordinates on this sphere. This works similarly to the way longitude and latitude work as coordinates to describe places on Earth. So what we have here are two sets of 3 numbers each. One of the sets is called right ascension and the other one is called declination. Now declination is where a star is above the celestial equator. So yes, the celestial sphere has an equator and that is aligned with Earth's equator. And the declination just tells you how far away a star is from that equator. If a star has a positive declination, that means it's that many degrees above the celestial equator, and if it's negative, it's below. Right ascension is similar, but in the other direction. A right ascension gives you the direction of the star along the equator. So imagine looking at the celestial sphere from above, from the north. Right ascension is just the direction in which a star lies. If we flatten out the celestial sphere into a map similar to the Mercator projection, then right ascension becomes the x-coordinate and the declination becomes the y-coordinate on that map. It's not that crazy. But where it gets a little bit trippy is where it comes to the units of those two values. Right ascension and declination are just angles, but the units are a bit weird. That is why there are 3 numbers to each of those two. So right ascension is an angle, but it's not measured in degrees, but in hours. That is this first number of the right ascension. And the way this works is a full rotation around the celestial sphere is 24 hours, not 360 degrees. And it kind of makes sense because 24 hours is how long it takes for Earth to make a full turn, right? And so if the first number is hours, the other 2 numbers are just minutes and seconds for extra precision. Easy. One thing to watch out for is that it is not like a clock face. Sometimes in the military, people give directions by using a clock face as an analogy, watch out, you got a bogey on your 6. That is not what this is. A clock face only has 12 hours, this is 24 hours. And also a clock goes clockwise and the right ascension goes counterclockwise, because that is how Earth spins. And by the way, not that important, but in case you wonder, 0 o'clock on the right ascension is this line here. It's March equinox. It's one of the 2 points where the sun's path over the year intersects the equator. All right, so that covers right ascension. Now declination uses different units for some reason. Declination's main unit is not hours, it's just straight up degrees. So that's nice, but confusingly, the other 2 numbers in the declination are also minutes and seconds. It's just different minutes and different seconds. These are so-called arc minutes and arc seconds. Basically, each degree has 60 arc minutes and each arc minute has 60 arc seconds. Go figure. But yeah, like with right ascension, you get a total of 3 numbers for the added precision. As you can imagine, sky is big and star is small, so you need to be precise when describing a star's position. One thing to keep in mind is that declination goes from 90 degrees, which is straight up from North Pole, down to minus 90 degrees, which is straight down from South Pole. So with these 2 coordinates, we can describe where a star is on the sky. In order to figure out where it is in space, we need a 3rd number. That is the distance of a star from Earth. And this is this 3rd, or I guess 7th number here on the table, and that is measured in light years. And with that, we get a full set of so-called spherical coordinates, which we can use to convert to Cartesian coordinates. So now we need a function to turn these weird numbers into useful numbers. So first of all, let's turn those numbers into degrees. It would be nice if it was just a number, a single number, not 3 numbers, right? Now, I'm not an astronomer, but luckily we have the Mathematica code here, and we're going to absolutely use this. So the Inductiveload, the guy who made the person who made this beautiful code, actually has some code in order to convert these numbers into degrees. And the two angles that result are theta and phi. And so we're going to take his code and we're going to adapt this to Picotron. And again, this is just taken straight from the original code. So we have ra to theta and declination to phi. So ra means right ascension, right? So this is the basic x, this is y. And you can see, so we have take the hours, we multiplied by 15 because 360 divided by 24 is 15, right? There's each hour is 15 degrees, is what I'm saying. And then the minutes and seconds, and that results in a 300, like a circle is 360 degrees. That's degrees. That's not the unit that we're using in Picotron. We're gonna change that in a second. And then declination is here. Now I actually modified his code a little bit because he did a plus 90 here, and I don't think that works with the kind of like transformation we're gonna do in a second. So this is a bit different, but it's the same thing. Declination actually already uses degrees as a unit, so we can actually use the d as degrees. One thing to keep in mind is that declination can be positive and negative, because depending on that, the minutes or seconds have to be added or subtracted from the declination, because you know, if you have like minus 1.5, the 0.5 is this subtracted from the 1 and not added to the 1, right? So you cannot, that plus changes depending on whether you go negative or positive. So let's go for a ride. Let's go 4s in all star list do. By the way, we also need to include Astrolua in our main code. That means that this tab is just part of the main program, just including it in here. Okay, so we're running through the star list, and for each star list, we want to create a star. Let's actually execute the main stars here, because we're actually not doing it right now. So let's do make stars here. And then we're gonna delete our current stars. All right, so let us go like local theta. So that is going to be ra to the right ascension. Theta is going to be the x coordinate, so to speak, the x angle, right? So we're going to go s, ra to theta s. S, let me think about this. That's a bit inconvenient. Let me extract the right ascension. So RA equals S1. That is going to be this set of coordinates, right? That is the first entry in this object. That's right ascension. Now let me extract declination. That is going to be the second set of coordinates, right? This one. That's going to be this. Now ra to theta is going to be ra1. And you know, we could make it a little bit more convenient. We could, for example, make it so that ra to theta actually accepts an array as a parameter, but for now it's fine. So that gets us the theta. That's going to be the first angle, and the second angle is going to be phi. Again, it's not quite phi. It's slightly different than phi because we don't doing. It's fine. It's fine. It's gonna be fine. It's gonna be fine. Okay, fine. Let's clarify this real quick. So the original Mathematica code has a 90 minus at the beginning of the phi calculation. This is because the original code calculated the so-called polar phi angle, the angle between the vertical z-axis and the star. So at an angle of 0, this would mean that the star is straight above you, and at an angle of 90, it would mean that it's at the equator. You might notice that is not quite how the declination number works. The declination is the angle between the equator and the star, so it's the other way around. So the author of this Mathematica code put a 90 minus in front to convert one into the other. I decided that I know better and decided to make my life harder and change this to follow the definition of the declination number. And this is apparently called the latitudinal angle. And at least to me, this one made more sense. And of course, this will come back to haunt me later down the line. A little bit of foreshadowing. Let's just move on. That's going to be declination, declination, declination. Okay, so now with each of the stars, we're getting those numbers, those 3 numbers each, and we're converting them to degrees. And then let's go also let's go also with a distance. That's going to be S3. Now we're going to go local new star equals, and that's going to be our new star, and that's going to have an X, Y and Z position. And now our goal is to take those angles and turn them into Cartesian coordinates. But whatever happens at the end, we're going to do add stars, new star, right? All right, so now all we need to do is find out how to turn those angles into Cartesian coordinates. Now, luckily, this is math. This is just basic math. You can look up on the internet how to convert spherical coordinates into Cartesian coordinates, how to convert two angles into three-dimensional positions in space. That's very simple math. It's kind of a little bit similar to this equation, a little bit similar, but not quite. And I can just like spell out what it is. It's distance multiplied with cosine of phi. That's the x position, multiplied by cosine of theta. And yes, of course, I was using a slightly different reference for this formula, and this one had the equation for x and y swapped for some reason. I don't know what happened there. Of course, I haven't noticed at the time. As we saw before in 3D space, the axis labels are a bit all over the place anyway. There's, different ways to skin the cat here. So it is not the end of the world, but let's put a pin in that because this might be also the source of an issue that is coming up. But don't worry, we'll figure it out in the end. It'll be fine. That's for the x-coordinate. For the y-coordinate, it's distance of cosine of phi multiplied by sine of theta. And with the sine, we need to be careful because Picotron and Pico-8 the signs are inverted because y goes down on the screen. So sine is different than the regular sine, so we have to do a minus in here. So that's x and y, and then the z is going to be distance times, again, minus sine phi. That's all there is. That's all there is. That will create us our stars. Will this work? Hey, did I promise too much? Did I promise too much? Now, okay, we have to verify if this is correct. We have to verify if this is correct because we don't know. We just took some numbers and put them through some functions that we took from the internet, and it made brrrt, and we don't quite know if this is the real star system. Are these the real stars? And so we're gonna actually remove some of the stars here and just want to look at two stars. So I just want to have Alpha Centauri and Barnard star. That's the only stars I want to be looking at, and there's good reasons for that. So let's see, let's look at this. I already see some problems. So Alpha Centauri is looking up. It should be looking down. Off to a bad start. Alpha Centauri is downwards from us, so we messed up some of the y coordinates. Let me look up where the problem is. This is a little bit silly, but we forgot that we're working in degrees. But we need to be working with Pico-8 degrees. So we need to go theta equals theta divided by 360 because a one rotation is 1 in Pico-8. And then phi equals phi divided by 360. Oops. Now this is still wrong. This is still not right. Let us find out whether x is positive, or like, is this something that we messed up with Astro, or is this something that we messed up in our projection? So let me add an edge that goes up. So let me just add an edge that goes up. Add edges like this. It is going up. We messed up the conversion. I see the problem. See, we used ra to theta for both angles. We need to say dec to phi for declination. That's awkward, but there we are. Does that look fine? It doesn't quite look right still. There is one problem that I'm flabbergasted by. See, the reason why I'm using Barnard star and Alpha Centauri, I know that Alpha Centauri is downwards, and I know that Barnard star is slightly above the plane, slightly above this grid. But also I referenced the image that the other guy on the internet has created. So if you look at this image here, you can see that if Alpha Centauri is looking at you, like it's kind of like pointing towards you, then the Bernard star should be on the right. And that is not what is happening right now in our image, it seems like. So if Alpha Centauri is looking at us, Bernard star is to the left, it should be on the right. But I think the problem is actually rotational stuff. I think we're getting a bit of an illusion problem, that there's like an illusion happening here where we don't quite see where front and back is, because if you rotate it like this, let me see. If we rotate it like this, if we imagine that this is now downwards, then that would be correct. Front and back are just switched. So let me just move things around a little bit. Let me move things around. Here, where we do, when we apply the rotation, we're just gonna go minus and plus like this, boop. And I think this should give us what we need. There we go. All right, so this is correct. This seems correct to me. So now Alpha Centauri is looking at us, and we have Bernard star to the right. Let me maybe start in a certain, like this is a good perspective to start in. So let me put these as our starting values for all the rotations. So -1, 2, and 3, and 6. There we go. Let's put in these numbers here. I think this looks good. This looks like kind of like isometric. It's kind of like almost exactly the same, the right kind of angled for it to feel like pixel art isometric. As you can see now when we rotate it, now Alpha Centauri is looking at us, and we have Bernard star to the right. Now, the nice thing about this, now that we finish with this, the nice thing about this is that you can go now on Wikipedia and you can put in any star that you want, and it will appear here in our solar system, in our little star map. For example, one thing that is worth checking now is to make sure that we're actually aligned. Like if the Polaris star is actually on top, the Polaris star should be always in north, so it should be exactly in the center of the sky, right? So let's put in the Polaris star. So this is Polaris, and as you can see, if you go on Wikipedia, you can see the numbers of Polaris. I'm going to take them. Now, the problem with Polaris, you will see very quickly. Where is it? Where is the distance? Yeah, distance is 446 light years. That's a little bit outside of our map, but we're going to put in the numbers, and we're going to see if it appears on the top. Right, so let's put it in here. So let's put in Polaris in here. So that's gonna 2 hours, 31 minutes, 49:09. And again, the distance is 446. Oof, that's gonna look weird. Oh, there we go. That's Polaris all the way up there. Okay, it's a little bit far away. So let's put it a bit closer, 20 light years. And yeah, it appears pretty much dead center above us. That's what we wanted. All right, so I can now remove this debug that I had here, this edges debug. So now we see Polaris all high above us and those two stars that we talked about next to us. That's nice. Now let me clean this a little bit up. All right, so let us now remove Polaris. We don't need, we kind of verified that we're getting the right kind of map. Let me bring back all of the other stars and talk a little bit about information design. Right, so if you run this, you see that we have a whole bunch of dots, and that's great, that's good stuff, but also it's kind of difficult to, like, what is this? What am I looking at? It would be nice if I could click on stuff, and also it's visually a little bit difficult to parse. So let me tweak the colors a little bit. So for one, I want the edges to be actually dark blue, and about them, oh no, that's wrong. I want them to be dark blue. So we get, yes, this is, they are no longer as obtrusive. Now the stars kind of pop a little bit more because the edges, this grid is no longer as extreme. And we can make the stars just a little bit smaller in general. I think 2 is a little bit big for those stars. Let's make them 1. Whoops. There we go, the radius 1. So now the stars are tiny little dots. And maybe the color of this vertical line is not quite great. Let me pick something darker. I mean, 21 would be the better color here, but we're gonna have some problems with Pico-8 for this. All right, so this gives us a bit of a nicer image. It's less noisy. We can focus more on the stars. We see the stars now. So this is the point where I wanna show you that this is absolutely something that you can also pull off in Pico-8. So let's move over to Pico-8. Here we are. So I'm gonna save right away as star map. And let me just copy over the code. Boop, boop. So I just straight up copied the code. I'm gonna run this. It's gonna be a problem here. There's an include here that we have to get rid of. Let's see what else happens. There is no mouse function. We have to invent the mouse function. So let's write us a function that is about mouse function mouse, and it's gonna do the following: return stat 32 stat 33 stat 34 stat 36. I'm not sure if 36 is correct. Let's do 36 for now. And we also need to poke in the def mode, because the mouse stuff doesn't work in Pico-8 unless you do something at the beginning here, and that is going to be this. Boop. Like this. All right, so let's run this. There's a problem there. 1 comma too much. All right. The mouse is working. We don't see anything because obviously this screen is now a lot smaller. So we need to change things into 64 in here. And look, it's the same thing. It's the same thing. Isn't that sweet? Now, obviously, it's kind of difficult to control this because we don't actually see the mouse cursor. We'd have to actually draw the mouse cursor for this. Let me draw the mouse cursor. At least a little dot here. So now it's a lot easier. So you can see the same thing works in Pico-8 as in Picotron. It's the same code. There's nothing special that we're using. It's just math. It's just math and drawing lines and circles onto the screen. Isn't that nice? You can have a 3D map in Pico-8. It's so powerful. All right, back in Picotron. So let me make sense a little bit of the star map so we can understand a little bit what is happening, so we can understand the astronomy underneath a little bit. These are just dots. What do those dots mean? How can we structure them? How can we make sense of them? I want to add 2 things, and we're going to wrap this up for today. So one thing I want to add is I want to be able to like hover over the stars, and I want to see the name of the star. So this is the way we do this. Is when we draw the stars, we're going to just find out which star is the closest. So we're going to go local close s equals nil, and local close dist equals 999. And then when we're drawing the star, this is where we're drawing the star, right? We're going to go, we're going to calculate the distance between the star on the screen and their mouse position. And for this, we're going to use a distance function. I'm not sure if Picotron has this built in, but this is a well-known function. We used this many times before in Pico-8. This is just your Pythagoras theorem thing, right? It's just the distance between two coordinates. So we're going to use this function here to calculate the distance. So if we're going to call local d equals distance between the coordinates on the screen, so P1, P2, and mx and my. So between the coordinates on the screen and the mouse. So if the d is smaller than close dist, then close, let's go close star. Close star equals S, and then close dist equals D. Right? And then when we're drawing stuff, we can go if close star, if this exists, if there's a close star, then. And then I'm just gonna draw. I'm gonna draw the name of the star. But the problem is that we are not actually storing the names of the stars. We can just add a fourth entry in our star, and that's just gonna be the name of the star. So that's gonna be 1, 2, 3, the fourth entry here as well. So we're just gonna put the fourth entry in our star list into the star as well. And then we're gonna go print. Now the problem is obviously that when we're printing the caption of the star, we have already projected the star, so we have to reproject the star kind of. So let's do that real quick. So we're gonna go local p equals project close star. So we find out again where the coordinates are of the star are on the screen. A little bit redundant, but whatever. And then I'm gonna print it at this location. So So we're going to print the name of the star. That's the fourth entry on there with very bright colors. Let's see if this works. Hey, see, it's working. It's working. Now let me beef this a little bit up. We're gonna go circ. I'm gonna put a circle around the star that we are currently selecting because it's maybe a bit confusing. Radius 4 and color 7. Let's do something like this. So now you can see now there's a circle appearing over the star that we're hovering above. That's nice. That's nice. That's very good. And then it's a little bit jumping around a little bit. So let's make it so that if D is also smaller than 8. So it's like we have to be really close to the star to actually highlight it, right? That's nice. Now the caption, let's move the caption a little bit so it's a little better readable. +4, -3, something like this. +6. Yeah, +8 even. Yeah, see, now we're talking. Now we can actually really explore this map and we can actually point to the different stars on our star map and so forth. Peachy, good, excellent. The other thing I want to also do, this is a little bit geeky part, but I kind of really want to do it because right now it's just dots. They don't mean anything. And we are here to learn something about our stellar neighborhood. So I actually want to color in the stars to kind of like indicate how big and small they are and what color they have, because there's actually some interesting insight, astronomical insight about our neighborhood stars. So I actually did some research. So I'm going to paste this in and you can, I will share the source code with you so we can see what's happening. Why do we have, All right, I cleaned this up a little bit. So each star I provided with some additional information. So whether the star is big or small, big meaning something around the star of our own sun. That's considered a big star. And there we can see there's a lot of stars that are actually a lot smaller than the sun in our neighborhood. And those are small. And then also color, right? They're not necessarily the color, like it wouldn't be like red when you saw a red star, but there's a bit of a spectrum shift, right? And we call them red and orange and so forth. Our sun is kind of like yellowish, but there's also brighter stars than our sun, and those will be more whitish. And there's a lot of stars that are dimmer than our star, and those will shift into the reds or oranges and then reds. So I kind of like try to encode this a little bit, so we get a little bit more variation in those stars. So it's not just like dots. So the dots actually mean something. All right, so first let's encode let's add to the stars some extra information. So we're gonna go S5 and S5 equals small and 2 or 3. So it's gonna be a 2 radius for a small star and everything else is gonna be 3 radius. So we're gonna see a little bit of a size here. That's gonna be the 5th entry in our star, in our own star, the stars map here that we have here. And we're going to take that and we're going to use this to draw the circles. So here's where we're drawing the circle, and instead of the radius 1, oh wait, it's radius 1, right? Let's go 1 or 2. Or yeah, 1 or 2. Let's see how that works. So instead of the 1 here, that's every star is the same size, we're going to go S5. Let's see how this looks. Oops, there's a problem here. There we go. So you can see now there's some big chunky stars here, and our sun is actually one of the chunky stars. And we're going to talk about the chunky stars in a second. I'm gonna walk you through some of the interesting entries in here. And the other thing is I want to encode the colors as well. So let's put this as our 6th entry. For now, let's do like a random. That's going to be fun. We're going to have some colorful stars. And then instead of just like yellow, we're gonna do this as 6. And now we have like beautiful, colorful stars, but obviously that's not the stars, not the colors that we want to show. But I want to actually take this data that I have here and I want to use that data. So this is going to be red, orange, yellow, and white. So and brown as well. So these are different different colors. So let's go local call. It's going to default to red. What kind of color did I choose? I've written down some colors that work very well. So most of the stars that we're going to see are going to be 24. That's going to be this dim red color. And we're going to see in a second why that is. And then if it's white, so if S6, if that's white, then in this case, I want the color to be white, 7, right? And then else if that's, let's see, orange, let's go yellow. If that's yellow, then the color is gonna be obviously this one, 10. And if it's, what else? Orange, let's go orange. Then we want to maybe have this one, 9. Orange, yellow, red, white. I think brown is not. So that's a brown dwarf. For this one, I picked 20. That's going to be this color. No, it's this color, 20. Yeah, that's very brown. So let's run this and let's see. And let's put this into our star. And there we are, ladies and gentlemen. Here are some of the beautiful, beautiful stars in our stellar neighborhood. Let me walk you through our stellar neighborhood, shall we? So obviously we have our sun in the center. That is a nice big yellow star. Here is Alpha Centauri and also Proxima Centauri. So this is a bit of a weird thing because they're very close nearby. So Alpha Centauri is a binary system. There's a big star and a smaller star nearby. And also there's Proxima Centauri, which is kind of part of the system, but not quite. It's kind of very far away from those two, but also it's pretty close in the grand scheme of things. So it's not clear whether it's a triple solar system or if these are two separate ones. They can be observed separately from each other. So they kind of so these are the three most nearby stars. And they have exoplanets. There's planets that we discovered there. There's very interesting videos that you can watch about this. This is Bernard star that I really like because it's also very close and it's also close to our equator, to our celestial equator. Something that I like about Bernard star is that it has been a subject of a study called Project Daedalus, which was a study on how to figure out the feasibility of traveling to a nearby star. And they picked Bernard star, which is otherwise a star that you see a lot in here, which are these red, faint red dwarfs. There's a lot of red dwarfs in our neighborhood, which are smaller than our sun, a lot smaller than our sun, and a lot dimmer than our sun. So that's why it kind of really helps making them smaller and dimmer, because you can tell that which stars really stand out, right? And then, for example, a very important one is Sirius here. So why is Sirius? That's a very bright star, brighter than our sun, very bright on the star. I think the brightest star on the sky. And that is actually a binary star. And I think one of the stars that is there is actually a white dwarf. Now over here, look at this. What is this? That is a nice little yellowish star. That just seems to be similar to our own star, huh? Yes, this is Tau Ceti. And if you are going to be watching a science fiction movie that comes out in the future called Project Hail Mary with Ryan Gosling, that will take place in Tau Ceti. They will travel to Tau Ceti in that science fiction movie. And for good reasons. It's a very interesting system. It looks kind of similar to our own system. Very, very promising. And also not far away from there is also Epsilon Eridani. Now this is colored orange here, I'm not quite sure why, but I think this is also one of the very famous solar systems from different science fiction movies. I think, correct me if I'm wrong, but I think this is the place where Halo Reach is actually orbiting, right? So that's where the planet Halo Reach is. And also I think this is also the place of the famous space station Babylon 5. So that's where Babylon 5 was taking place. And obviously, who can forget? Who can forget? Here above somewhere, I think. Where is it? Ah, there we go. It's not up, it's actually here close to the equator. So that's Wolf 359. If you're a Trekkie, you know very well that this is the battle, the place where the battle against the Borg took place. A very devastating Star Trek battle took place in here. And you can see it's right at the doorstep. It's right near the solar system. So this is our star map. As you can see, it's just a starting point. It's just something to get you started, right? And now you can use this, for example, to create a bigger star map. You can easily take stuff from Wikipedia and add to it. You can just use the celestial coordinates that are readily available to expand the star map to make them bigger. You could also add more information about those stars. It would be nice if I could just like click on the star and see some information about it. Maybe like a little diagram showing me the solar system a little bit, maybe some information about the star, maybe if it has exoplanets, maybe showing the star size compared to the sun or something like this. That's possible. Also, I think the visualization still could be a little bit better. Something that I don't like is that it's kind of hard to judge whether a star is below or above the grid. I mean, again, I made it interactive so we can play around with it. And as you move it around, it kind of like snaps into place visually. But once it stops moving, it's kind of like becomes just a bunch of lines and dots. So something you could do is just render the stars underneath the grid first, then draw the grid on top of them, and then the stars above. Another thing you could also try is to make sure that stars that are far away are a little bit dimmer, so it can like get a bit of a perspective effect here. There's a lot of things you can play around with. Something I also tried is like connecting the stars together to kind of like constellations, not like real constellations, but like nearby stars would have lanes between them, so they kind of like clump together. That also helps to structure the space around this. There's a lot of things that you can do here, but I'm going to leave you with this for now. Let me know in the comment section, what would you like to see me try with the star map to enhance it and make it even better? I'm down with making a second video about this to improve this, but let me know what you want to see. And of course, the code will be available for you. I will actually upload maybe this to Lexaloffle so everybody can access this beautiful, beautiful star map. And this is it. Thank you so much for joining me, and thank you so much for everybody who's been supporting this channel. You can also support this channel on Ko-fi.com. The address is ko-fi.com/lazydevs. One thing that you get as my Ko-fi supporter is a bit of an insight into the process behind creating this channel. Currently, I'm kind of like figuring out what big project to start next. I am definitely interested in Picotron and its capabilities. That's why I'm doing those small videos showing you what Picotron can do and cannot do. This is also for me, so I can understand how Picotron works, so I can maybe do a more comprehensive tutorial series on doing a big project with Picotron. So yeah, I can imagine maybe working on some kind of strategy game, some kind of space exploration games. That's also definitely in the cards. We're gonna see about that. For now, watch this space. See you next time around, guys. Bye bye.